Okay, so welcome to this lecture extra, which is looking into the seaweed growth and survivorship lecture that I did last week. And it's really looking here at how algae respond to external stressors, such as abiotic factors, and in this case we're looking at light. So the most important thing here is I've got this kind of figure from Lebanon and Harrison, or the second volume of Lebanon and Harrison, which is chapter 7. It shows quite neatly how stress is not just one single component. We have severity of stress, i.e. the level of stress that is actually occurring at that given moment and given time. We also have the duration, so how long did the stress event last for, could elicit different responses from an organism. So it's not just being hit by a stress, it's also about the length at which you are exposed to such a stressor. Now, during time, there's also the extra factor to think about, which is how frequent are these things? Do they happen on a regular basis? In which so would you expect that an organism would be adapted and be able to regulate and respond to such stress? Or is it a random or stochastic event which has caused an initial pulse, for example, which has driven the organism that we're looking at over a particular threshold in which it can no longer respond? But also, when you think about it, you need to think about the interactive effect of stresses, additive effects. So do two stresses combined have an equal response from an organism, or is it a much more amplified response to that organism? So those things, when you think about how an organism is going to respond to stress, you need to take into account those stress characteristics, severity, duration, the number, frequency, and abundance of exposure, as well as a combination of multiple stress factors, might actually drive different responses to what might be, for example, a very predictable singular stress. Now, the organism will respond in different ways. It may, depending on where the stress is actually acting upon, it might be localized in the response. But if you're a young germling, you might find that you are really at the mercy of the environment, and therefore you're much more likely to succumb to stress. You can't regulate, you can't fight against it. But also you may find that there's some genotypic adaptation, but there might also be plastic responses, whereby the same genotype may exhibit different responses in response to different stresses. So when the organism encounters stress, there's several different responses that it might go through. Resistance or susceptibility. So you need to look at these two things as slightly different ways of how they respond. So I've labelled these here A and B, and as we move to the next slide, you can see I've carried this on just to illustrate it. So some organisms can resist, and this is B, and I've shown it in this schematic graph here, is that you expose an organism to a stress, you will have an initial response followed by a period of adjustment, after which case, in a length of time, nobody really knows, it would be variable for different species, for example, will become acclimated to that stressor. Now, in some situations, when faced with a stress, it's the severity, the duration is just of so intense magnitude that we see this initial response, but we do not see a period of adjustment. We just see cell death occurring, which means that that organism is not able to respond to such a stress. And there's two generic ways that an organism might respond. First one is the conformer. The conformer will just track the stressor condition. Now, body temperature will increase with external temperature increasing. A regulator, for example, would be able to adjust the temperature inside their bodies in order to maintain a regular level. That's known as a regulator. Endothermic organisms, for example, are an example of such a regulator. An example of a regulator in a seaweed I show here using this short-term responses to salinity change. So you can see that we have two options: salinity change that increases or decreases, and how the alga responds depends on different species, but essentially they will all follow a very similar pattern, and you can see how they respond to these different conditions. Now, if they can't deal with the stress, then they end up with damage, okay, which is a key thing to think about for when you're looking at regulation. So that's actively changing the internal concentration of whatever to match the external in order to avoid being damaged by the conditions outside. So you're not matching the external, but you are really attempting to adjust in response to the external condition. A conformer, for example, would actually be tracking and matching the external condition. And a good example of this is Pelvicia canal iculata, which is a very, very high shore species found throughout many shores in British Isles, and it's really at the top of the shore, so it's a very, very dry. It spends a lot of time out of water, and it can survive for many, many days without immersion. But it becomes so brittle and so dry, it's almost completely desiccated. But once it's hit by seawater again, it will revive. But that's an example of a semi-conformer. It's actually tracking the condition. It's drying out with the lack of seawater. But if you submerge the species for more than 6 hours out of 12, it will just start to break down and die. So it's one of those species which is very well adapted for the environment that it's in, but not very well adapted for varying conditions that might affect it. So, when we look at light, we covered some elements of photosynthesis, which I won't go through in here, but I will move on to what happens to light in the ocean. It's vitally important that you are aware that light is significantly attenuated as you go deeper. And that's because plankton, sediments, waves, bubbles, and so on, all absorbing light from when it's in the water. Okay? Now, it's not only just about the bulk amount of light, it's also about the spectral quality of light that is actually striking the different depths. And as we go deeper through the ocean, you see that blue light is the one that penetrates the furthest. Other wavelengths are rapidly attenuated. So throughout time, we find that 90% of the total annual irradiance reaching the sublittoral habitats around Northern Europe occurs during April and September. Now, as you go deeper, you'll find that there's an exponential loss. For example, at 8 meters in this particular study, by Lunan and Dring, we find that only 0.7% of the surface irradiance hits a kelp limit, which is the lower limit of kelp. So it's quite dark, and we're looking now at laminaria hyperborea. As you go deeper to the real low limit of algal distribution, 15 meters water depth, we see that corresponds with 0.05% of the surface irradiance. And that means that algae have to be, especially the sublittoral ones, they have to be very well adapted to light, and the lack of light in particular. Now, light not only varies through the annual timescale, but also through a daily timescale, especially where you have tides. So you could have large fluctuations in the tide, the turbidity that's being driven by the tide, as well as clouds, and over the natural day-like cycle as the sun passes over the top. You can see very, very big differences in the amount of light occurring. So algae has to adapt not only to long-term, but also to medium-term light environments. So as we go even closer, we now look at, this is just a study on 120 seconds, 2 minutes of observation. We see that the light condition at the surface is very, very consistent. However, when we go to 1 meter depth below a canopy, we see huge fluctuations in light intensity. As we go ever deeper, we see that can become fairly smooth again. Now that's because the canopy is moving, and this picture here illustrates how light can fleck through the gaps in the canopy and illuminating the turf. So in some cases, algae may see just too much light. This here is an example from Gerard in 1984, showing how the kelp is a super competitor, dramatically reducing the amount of light that reaches the benthos. And that is really, really important in ecology, because the light exclusion really does control what other organisms are growing in that environment. And there's an example here of Astrophyllum nodotum, which is a really, really good canopy that absorbs a huge amount of light. So here, This is a PE or PI curve which demonstrates responses of organisms to light. On the x-axis we have irradiance. On the y-axis we have the photosynthetic rate. It could be growth, it could be oxygen production, carbon dioxide consumption, for example. It's built up of several key things that we're going to look at. So the first one is Pmax, which is just the maximum rate that an organism can photosynthesize. The alpha is the rate at which an organism can reach the maximum level of photosynthesis. And by rate here, I'm referring to the amount of light. So you may find that some shade-adapted species can respond very quickly to limited amounts of light. We have compensation. This is the point at which above it, the organism is in net growth, net energy accumulation. Below it, they are in net respiration, they are consuming resources rather than producing it. They are the main tenets you need to take away from that. Also the photoinhibition one, where we start to see a quenching of photosynthesis. It might be due to damage, it might be due to regulatory mechanisms within the alga. So many species have very, very low compensation points, and that tends to reflect where they're found. They want to very quickly reach a point at which they are in net photosynthesis or in net energy accumulation, because the light environment is so variable. If they require very, very huge amounts of light, for example, which are only available for a very, very small amount of the day, then their overall productivity would be really low, and they would really struggle to survive. The saturation, i.e. Pmax, you find that can be much higher for canopy-forming species, rather than those which are deeper or those which are turf formers. So you need to think about where you might see different species and where they are, and that would reflect the light environment that they need in which to grow. So here we've got a study from Johansson and Seaweed in 2002, and we've got different functional forms of algae. Functional forms were covered in the first year organismal diversity lectures. So sheet, really thin, light can penetrate all the way through the cellular body. Filamentous, string of cells end on end. Coarsely brown, quite thick, and thick leathery, which are obviously the kelps and fucoids that we find around our shoreline. So there was a faster alpha here for species of a similar functional group, but which were found deeper. So the thick lines show deeper growing species. We can see a very, very fast alpha. They're reaching photosynthetic max quite quickly compared to their similar species, similar functional groups found in shallower waters. And there's several reasons for this. And the first one is that often deeper species have larger antennae, which allow them a bigger target, as it were, for light to strike and then for energy to be taken from that photon and used in the carving cycle. So they have larger ones. But it does mean that, although they might have larger antennae, it means that they get struck by so much light in certain conditions. So they would undergo what's called NPQ, or non-photochemical quenching, which would be a mechanism to remove that excess energy. It wouldn't be used, it would just be dissipated. Whereas shallower species tend to have smaller antennae, which means that they can get struck by a lot of light, and therefore they would not get quenched that much. And you can see in the picture here how the larger antennae maximize the amount of light striking, but lead to very, very high levels of NPQ. Whereas smaller antennae here allow lots of light to strike all the way through the alga, meaning that more antennae can pick up that light and less incidences of NPQ. So that's a really important adaptation, and algae can acclimate by changing the size of their antennae, the amount of them, as well as the pigmentation which is attached to these, in order to maximize the amount of light they're going to get. That leads me to accessory pigment. So algae do not just have chlorophyll A, they also have different accessory pigments that allow them to take in more advantage of different wavelengths of light. depending on the colour of the alga and weather. Now, in some cases you have far too much light. That leads to what's called photoinhibition, whereby you're being struck by so much light that you have to get rid of that energy. And MPQ is the mechanism by which some algae utilise that. Others will just shake themselves to death. And here we have an example of Palmaria decipens, the decipiens, which is using, I assume, some kind of MPQ type mechanism in order to dissipate energy as the light environment becomes too maximum. And you can see during the middle of the day it is very much inhibited, so it's not optimally photosynthesizing. If you desiccate it and give it additional stress, we see even lower levels, so that there's lots of different elements of stress that could be a problem for intertidal species. So I hope that helps, and I've covered some of the major points that I think you should be looking at. And you really want to think about stress as not just a singular concept, but as a multiple parameter. And I think that is the key thing that you need to bring to the forefront of your mind, is that stress can comprise of different characteristics which can affect how algae and other organisms are responding to it